Welcome to Next Gen Manufacturing. Today, we're diving into something that sounds kinda crazy, how a science from 400 years ago is the engine behind our most futuristic technology. We're talking robotics, hypersonic jets, you name it. It's an old science, but believe me, it is building our tomorrow.
So that's the big question, right? It feels like a total paradox. How can the same principles that Isaac Newton was working with be absolutely essential for designing the robots that will build our future? Well, let's break it down.
The answer, it turns out, is a field called general mechanics. And while the rules are classic, their application has never been more vital. This isn't some dusty textbook science. It's having a massive comeback in robotics, aerospace, and high-performance vehicle design. It is the powerhouse behind it all.
So here's our game plan. We'll look at why this old science is suddenly so hot again. Then we'll get into the two main questions it answers and its key ingredients, kinematics and dynamics. And finally, we'll see how it all clicks together to build the future.
Okay, let's jump right in. An old science's new power. And I want to be clear, this is not a history lesson. This is about a tool that engineers are using right now to solve some of the most complex challenges we face today. I love this quote from Professor Jean-Pierre Brassard because it boils the entire massive field down to one simple idea. It's all about figuring out two things. One, how a system moves, and two, what forces are making it move. That's it. It's really just two sides of the very same coin. And that one goal creates these two fundamental questions that mechanics is designed to answer. The best way to think about them is as opposites. They're inverse problems, where one starts right where the other one leaves off. Okay, check this out. On the left, you've got problem one. This is where you know all the forces. You know, gravity, wind resistance, the power from an engine, and your job is to predict what's going to happen. If a driver yanks the wheel, does the car turn or does it spin out? That's problem one. Now, on the right, you flip it. You know the exact motion you want, like a robot arm following a perfect path. And you have to figure out the hidden forces your motors need to create to make that happen. So let's make that second problem a little more real. I mean, how in the world would an engineer calculate the absolutely massive forces twisting a pro golfer's wrists during a swing? It's a perfect example of starting with the motion to find the hidden forces. It's actually a super cool three-step process. First, you observe. You film the swing with incredibly high-speed cameras to capture every tiny detail of its position, its velocity, its acceleration. You get all the data. Second, you model. The human body is way too complex, right? So you simplify it into a model you can actually work with, like a double pendulum for the arms in the club. And finally, you calculate. You write the equations of motion for that model. And since you already know how it moved, the forces and torques are the only unknowns left. You just solve for them. It's like detective work, but with math. Now, to do any of this, engineers have a toolkit, and the first tool is kinematics. The best way to think about it is as the language of motion. It's the geometry, the choreography. It's all about describing how things move, long before we even ask why. And the key here, the really crucial point, is that forces are completely off the table. We're not talking about gravity or friction, none of that. Kinematics is purely descriptive. We're just mapping out the movement itself. Where is it? How fast is it going? And is it speeding up? That's it. Just the what and the how. So where this gets really powerful is in understanding how machines are actually put together. I mean, at their heart, most machines are just a bunch of solid parts that are connected to each other by joints. In the world of mechanics, they have a formal name for these joints, liaisons. And that word, liaison, is kind of perfect because it has two meanings. First, there's the physical part itself, like the actual metal ball joint in your car that lets the wheel assembly pivot. But second, and this is the really important part, it's the mathematical relationship that joint creates. For example, in an engine, the piston's up and down motion is mathematically locked to the crank's rotation. Kinematics gives us the precise equations to define that relationship. Okay, so if kinematics is the how, it's time to grab the second tool out of our kit. This is dynamics, and it's all about the why. This is where we finally bring the physics into the picture to explain what's causing all that motion we just described. Yeah, dynamics is the bridge. It connects the dots. It takes the how, that kinematic description of movement, and links it to the why, the forces and torques that are actually making it all happen. This is where we can write the fundamental equations that let us actually predict how something is going to behave. All right, now for the real payoff, let's take all these foundational ideas and connect them to the absolute cutting edge.
This is where we see kinematics and dynamics working together to design and perfect the technology that's shaping our future.
So what's the end game in the industry? It's one word: optimization. The goal is to use kinematics to choreograph the most efficient movement possible, and then use dynamics to calculate the exact forces needed to achieve it. It's all about wringing every single drop of speed, efficiency, and performance out of a system. And the applications are just incredible. We're talking aerospace engineers shaping vehicles for hypersonic flight. We're talking automotive engineers programming the stability control that keeps your car on the road. And in next-gen manufacturing, this is everything. It's how you program a robot to perform a delicate task with perfect precision millions of times. It's even used in biomechanics to perfect an athlete's form. Just look at this. A huge goal in aerospace is to beat air resistance, or drag. Using dynamics, an engineer can calculate the absolute optimal shape for a nose cone to slice through the air, minimizing that drag and getting it as close to zero as physically possible. And it's the exact same logic, just in a different context. For a race car, the goal is minimum time. Mechanics lets engineers calculate the perfect strategy, exactly when to accelerate, precisely how hard to brake, the perfect line through a corner, all to hit that finish line in the absolute shortest time possible. Which really brings us full circle, back to this quote. It's kind of amazing when you think about it. A science that is so ancient, with its roots stretching back for centuries, is at the same time so current, so absolutely essential for our most advanced technology. And that kind of leaves us with one last thought. It really makes you wonder, what other classic foundational principles are just out there, waiting for the right moment and the right technology to come along so they can solve the biggest problems of tomorrow?